If you have two wires that are carrying current and they can attract or repel each other, aren't they just magnets? So we're looking at force in this video, specifically with long straight wires that carry current and generate magnetic fields. The magnetic field around a long wire, you can find the direction of it using the right hand rule, which I've been talking about in the past few videos, where you grab the wire with your right hand and let's say the current's going this way, then you point your thumb this way. Your fingers will curl in the direction of the magnetic lines. From experiments, we found that the field strength B decreases the further you get from the wire. Makes sense, right? The formula for it is this, and it's on the free cheat sheet in the description below. But this is the permeability of free space, which is a constant equal to 4 pi times 10 negative 7. And the units for this constant is Tesla MOA. I is, of course, the current, and R is the distance from the wire. So actually, when you look at it, it's a pretty simple formula. This is a constant, 2 pi is a constant. What's left is the current and how far. And on the free cheat sheet, I'll include the constant for you. I think that helps. So let's go through an example problem. A vertical wire is carrying 25 amps of current. How strong is the magnetic field when you're 10 centimeters away? Because we already learned that currents can create magnetic fields. So using our formula, and let's just write out the constants from the start. How much is the current? 25. How much is the distance? In meters, it's 0.1. The answer for the strength of the field 10 centimeters away is 5 times 10 to the power of negative 5 Teslas. This is about the same strength of Earth's magnetic field. This is why wires that carry large current can throw off compasses that are nearby. Say we have two vertical wires, and this is an example problem. They are spaced 8 centimeters apart, and wire A carries a current of 6 amps out of the page or out of the screen. What does that mean, and how is that possible? Okay, when you have a problem in exams and when you see this in textbooks, a dot means it's coming out of the page, and X means it's going into the page. Let me try and visualize this for you. If the current's going up on this one and the current's going down on this one, let's pan over. Let's look at it from the bird's eye view. Okay, it looks something like this. The top of the wire, top of the other wire. This one's coming out of the page. This one's going down toward the ground, you could say. Does it make sense? It's coming out of the screen. It's coming toward you, literally toward you. So this one, wire A, like we said, it carries 6 amps of current toward us out of the screen. Wire B carries 4 amps the other direction. It's going away, further away from you, into the page or the screen. The distance between them, remember, it's 8 centimeters, and we want to calculate the magnetic field at the midpoint between them. How do we do this? You can imagine magnetic fields like this. They're circling around. Let's use the right-hand rule for each wire to find where these magnetic fields point. So, starting with A, imagine this is your thumb from top-down view. If you look at your thumb from above, this is what we're representing it by. When you grab onto this wire with your right hand, that's why it's called the right-hand rule, your fingers will wrap around it counterclockwise, which means that field at the midpoint coming from A points up. So we'll represent it with this arrow. And this is B1, because remember, B is how we denote the magnetic field. How about for the other wire? This time your hand would be upside down because your thumb has to go down to follow the current path, which means that your fingers would curl the other way because your hand is flipped. Since your fingers go in the direction of the magnetic field, this wire also pointing up. So that's how the magnetic field, you can imagine it. Because both fields at the midpoint are pointing up, and up means this way. It's a little confusing. You have to think 3D. Because they're both pointing in the same direction, they add up. So we can calculate the net field. You use the magnetic field formula near a straight wire. Remember, it's on the free cheat sheet in the description. It looks like this. With this constant divided by 2 pi multiplied by our current over the radius. The current in total is 10 amps. And the radius, 8 centimeters. But because it's the midpoint, the radius of these two magnetic fields would be 4 centimeters, which in meters is 0.04. Multiplied by this constant and 2 pi. Our answer is 5 times 10 to the power of negative 5 Teslas. That is the strength of our magnetic field right here in the center. Now for the next concept. Currents, they don't only create magnetic fields. They also feel the forces from other magnetic fields. So here's a setup. Imagine two wires that are carrying current. Each wire generates a magnetic field around itself. This field acts on the other wire, which creates a force. Let me teach you about Ampere's law. And this is where the name amps or A comes from, the measure of current. And this law, which is also on the cheat sheet, says that the field from wire 1 at wire 2 is equal to the field of wire 1 times this constant again, the permeability, free space, times current of 1 over 2 pi and the distance in between your two wires. Then the force that's exerted on the second wire from the magnetic field of the first wire is given with this formula. The current of the second wire times the length times the field of the first wire, and you can combine these formulas by plugging this in for B1 to get the ultimate formula, which is written as this. And remember what this is for. This is the formula that finds the magnetic force between your wires. The right-hand rule works for this as well. And here's how it works. If the currents of your wires are going in the same direction, then they will attract. The forces will make them attract. They'll move together. If they are moving in the opposite directions, so one's going this way, one's going this way, then the wires will repel. It's different to charges and magnets. Let's go through an example problem. Imagine you have two wires and they are 3 millimeters apart. They are each 2 meters long and each carry 8 amps. However, the current of 8 amps is in opposite directions. What's the magnetic force created between them? Let's use that law that we just looked at. So 4 pi times 10 to the power of negative 7, which is that constant, times both of our currents in amps. And since they're the same, it's just 8 amps squared times the length, which is 2, divided by 2 pi times the radius, which is in meters, 3 times 10 to the power of negative 3 meters. This gives us 8.5 times 10 to the power of negative 3 newtons. This is a real measurable force that's going to pull the wires apart. Now, if the currents were traveling in the same direction, it would pull them together. If you have a field near a wire, you would find it with this formula. If you have a force between wires and you need to find it, it's this slightly bigger formula. Here's an analogy for both. More current equals a stronger field. For this, it's like charges that are repelling and attracting. And remember, you can use the right-hand rule for visual navigation.